This is Lab 4, exploring the motion of an oscillating object. By analyzing a recording of an object attached to a spring, we can use Tracker to plot its position on the x and y axis over time. This visual of observed motion can then be used to create a computational model depicting the oscillating motion of an object, in this case, a mass attached to a spring. In the case of this experiment, both the mass and the spring are the system. We can then compare the experimental observations to the computational models to see how our models match what actually occurs. As well, we can calculate the energy components of the system throughout the motion. The fundamental physical principles of this lab experiment include Newton's second law, as well as the energy principle. In the case of this experiment, the total energy is comprised of the sum of the kinetic energy, the gravitational potential energy, and the spring potential energy. These individual energy components are calculated using the above formulas. We also look at the net force on the mass, which is comprised of the spring force and the weight force. These are calculated using the equations on the left. Additional equations used in this experiment are used to calculate the relaxed length of the spring and the spring constant, which is based off the equation for the period of oscillation. The constants for this experiment are 0.123 meters for the relaxed length of the spring and 6.83 Newton per meters as the spring constant. These values are given in the instructional video. Our data and observations begin with a given mass of 0.402 kilograms. I then set the blue tracker calibration stick from the fixed attachment point to the mass, which is a length of 0.70 meters. I then set the coordinate axis with the origin at the fixed attachment point in a degree tilt of -90 degrees. I then used Tracker to quantify the x and y position at equal time intervals. From this Tracker analysis, I was able to get a plot of the motion of the spring. Shown above is the y position of the mass over time. I used the data to set the initial position of the mass. Because the mass is released from rest, the initial velocity is 0. I then altered the code to reflect these vectors for the initial conditions. I also updated the mass for this experiment. For my initial model, I used the constants given from the instructional video. I then updated the L vector, specifying L, the direction of L, or L hat, and S, the distance between the relaxed length of the spring and its length at the specified time. I then updated the equations for the energy components. Finally, I set the initial energies to be equal to the formulas specified in the previous slide. I set the weight and spring force definitions equal to their respective formulas and calculated the net force as the sum of these two components. I then updated the mass's velocity based on Newton's second law. The position of the mass is calculated using this updated velocity formula. The updated calculations of the spring are the same as earlier in the code, and the axis is equal to L. The energy calculations use the same formulas as earlier. Their changes subtract the initial energy from the new energy value. I then have code to plot the change in energies over time, as well as the mass's y position over time. Here we see the outcome of the coding. Having used Tracker to mark and record the y-coordinate of the center of mass, shown in red, I then used the computational model in GlowScript to calculate the coordinates of the object's motion, shown in blue. These positions were plotted onto the same graph shown here. We see that there is some differentiation, but overall the positions follow each other almost exactly. The code also plotted the energy changes of the kinetic energy, shown in blue, the gravitational potential energy, shown in red, the spring potential energy, shown in green, and the total energy, shown in orange. We see that the gravitational and spring potential energy oscillate opposite each other. We also see that the total energy remains at 0 throughout the duration of the model, indicating that the energy principle is satisfied and no energy is lost or gained by the system. By calculating the average oscillation period from the Tracker data, we can run the model with two separate sets of data. The first is based on the x-coordinate average oscillation time and has a different spring constant and relaxed length of the spring. The second is based on the y-coordinate average oscillation time and has different values for the two constants as well. The x-coordinate based model is much closer to the original, but neither are a good match and deviate from the data the longer the model runs. There are several explanations. First, there is the possibility that the Tracker data is not accurate. However, because our first model fits so well, this is less likely. Second, the model does not account for drag force. Finally, the instruction videos are based on the spring bouncing relatively vertically. The video analyzed here also moves horizontally to a large degree. The calculations used to find the spring constant and relaxed length are based on the spring's motion in one dimension. Here, our analysis looks at motion in 2 dimensions. Therefore, the model will not be as good a fit when using these calculations for the basis for constants. In conclusion, this experiment allows us to analyze the motion of an oscillating object. By using Newton's second law and the energy principle, we can create a computational model that depicts the motion of a mass on a spring. We can then compare our model to the observational data. When using the constants of the spring calculated from motion of the spring in one dimension, we find that our observational data matches our model very well. When we use the constants of the spring calculated from both oscillatory motion in the x and y direction, the model differs in varying degrees from our observational data. Nevertheless, in all three instances, we see the energy principle being maintained.